Hello YouTube, how are you? So today here we are back in the park, and again I'm by the De Young Museum, the band shell, and the Natural History Museum. Over my shoulder there is good old Francis Scott Keyes, the guy who penned the Star-Spangled Banner. Of all the anthems in the world that countries have, the Star-Spangled Banner is one of the most difficult to sing, and good luck. Anyway, today I promised the last video I would talk about eigenvalues and eventually try to describe the Eigen matrix. So as a little preface to this, in science we believe there are only three things that exist in reality: I, you, and it. Now what it is quite the mystery. Quantum physics is kind of burrowing in on that now, and it's still sort of iffy as to what it is. In order to explain an eigenvalue, the first thing I'm going to have to do is talk about nuclear magnetic resonance. I'll try to keep it simple, but first, frequencies can be notated in one of three possible ways. A frequency can be cycles per second, the number of times that a wave goes positive, reaches zero, goes negative, and comes back to the zero reference point in 1 second. For instance, the note A on the piano is 440 cycles per second. Frequency can also be represented as what we call periodicity. Since there are 440 cycles happening in 1 second, if I look at one cycle, I put 1 over 440 and I get 1/440th of a second. And that's called the periodicity. The periodicity is starting at a zero reference line. A frequency goes positive, comes back to the zero reference line, goes negative, and comes back to the zero reference line again. That is one cycle, or one period. So periodicity is expressed in terms of fractions of a second. And periodicity and frequency are essentially reciprocals of each other. 1 over 440 cycles per second is the period, or 440 over 1 is the frequency. Another way in which both frequency and periodicity can be notated is in what we call wavelength. Sound, which we're talking about, travels at approximately, I've just rounded out, at 720 miles per second in air. So if I want to see what the wavelength of a single period of a cycle is, I would have to take a mile, which is approximately 5,200 feet, and divide it by the frequency to figure out the length. And as you can tell, the wavelength of a single sound of 440 cycles per second could be several hundred feet long, from here to the museum and back. So you divide the 720 feet per second into 5,200 feet to find out what the to get a marker, and then take the periodicity 1/400th of a second and see how far 1/400th of a second can go over that 5,200 feet. So 1/440th of 5,200 feet would be approximately the wavelength of that thing. So a frequency can be notated as frequency, as periodicity, or as wavelength. All three are actually equivalent to describing a pitch. Now to get to magnetic nuclear resonance. When I was in high school back in the dark ages of 1950 something, I did the latest cutting edge of science was magnetic nuclear resonance, and I did a science fair project. So I studied it, and I won the Illinois State Science Fair for my my project in magnetic nuclear resonance. Later on, it came to benefit me when I left college, graduated from IIT, and went into the industry and worked at Zenith Radio Corporation as then a lab tech for Dr. Julian Hirsch. Dr. Julian Hirsch was one of the pioneers at Zenith on magnetic nuclear resonance imaging. And so let me explain magnetic nuclear resonance. As you know, the Bohr model of the atom is that we have a proton in the center of the atom, a proton, sometimes a neutron, and an electron flying around the outside in an orbit, sort of like the moon around the Earth. As the Earth, there is an axis that the Earth turns on. There's an axis that the atom turns on, and that axis is not perfectly perpendicular. It wobbles. If I'm rotating around the axis of my index finger, if I wobble the index finger like this, we call that precession. So as the Earth is turning, it's also precessing. And for the Earth, I believe, to precess completely around one cycle, it takes approximately 26,000 years. Of course, atoms, it takes less than the blink of an eye. And these atoms, as they're rotating, they're also precessing. So think of it as a top. If I took a top and I spun a top really fast, the top usually stabilizes up straight and rotates, and then as it starts to go slower and slower, you notice the top begins to precess, and the precession gets larger and larger. The wobble gets larger and larger as it slows down until eventually it loses it and tumbles around. Atoms are designed to precess a little bit, and they're moving or rotating fast enough that they don't ever tumble down. We found out in a laboratory back in the 50s that if you take a very powerful magnet, actually I used from a radar system what's called klystron magnets, and I took two very powerful electromagnets. And if you take these powerful electromagnets and you get a very big, large Gaussian field, what happens is the electrons and the protons, or the atom, will line up with that magnet. Let's say I have a north up here and a south down here. The magnetic field of the atom will align with the fields of that electromagnetic field that you're creating. And if the electromagnetic field is very high in Gauss, you can actually cause that atom to lock into the magnetic field of your electromagnet and just precess or rotate like a top that's at nice full speed. It will still precess, but you can get the axis pretty much aligned with the magnetic field that you're creating. They discovered that if you take and wrap, let's say I have a test tube, and I put something like water in the test tube, and then I put that test tube in this magnetic field, the atoms in the water will align to the electromagnetic field and stay in one direction, fairly stable, and sit there and precess. We found out if we wrapped a coil of wire around that magnetic field at right angles to the magnetic field, if we then put a radio wave, a radio beam into that coil, that the radio wave would transmit, just as a radio wave would, into that water and around that water. That water would be encompassed inside of that coil. And what happens is if you start moving the radio wave that you're transmitting at different frequencies, like a specific channel, it turns out that as you start to move up and down in frequency, there will be a frequency that as you approach it, for, let's say, the hydrogen that's in, you have hydrogen and oxygen, the hydrogen atom will begin to, it has what's known as a resonant frequency. And what happens is as you increase the frequency of that radio wave in that coil, you will finally reach a frequency in which the resonance of that hydrogen atom is starting to get bucked by that changing electromagnetic radio wave. And since the magnetic field is holding the atom as tightly in one direction as it can, and the electromagnetic radio wave is striking at a right angle, tapping on the side like as if the top is spinning and you're tapping the side of the top, what will happen is if you tap it at exactly the right frequency, it will flip. It will suddenly process quickly and flip over. And then what happens is it will flip again, and it will flip again. And as it flips, as the precession causes the atom to flip upside down, every time that atom flips, it puts out a little radio wave of its own. And that little radio wave can be picked up by that coil and measured. It turns out that if you scan up and down the radio frequency, you'll find out that for hydrogen, this happens at a specific frequency. And it's dependent on the frequency of the radio wave and the electromagnetic Gaussian field. The magnetic field is very important. The amount of Gauss holding the precession in tow, essentially, causing the atom to align with the field. And then the electromagnetic radio wave coming in at right angles, hitting it around its equator and tapping it. When it taps it at exactly the right frequency, what happens is that atom will, the precession will get worse, it will wobble, and it will flip and become unstable. And if the frequency goes higher than that, it will, you move away from the resonant node of the hydrogen atom, it will stabilize again and be pulled back into the magnetic field. So it turns out if you take these signals, the transmitting signal and the receiving signal that you're picking up from the coil, and put it into an oscilloscope and set up the oscilloscope to get what's called a Lissajous pattern, you get a beautiful round circle on the oscilloscope where the X, Y, and Z axis are balanced in such a way that the oscilloscope produces this beautiful round circle that when you hit the resonant frequency of that atom and it processes and throws off a little packet, what happens is that round wave will suddenly fold and turn into a figure 8. And that figure 8 says we've struck the resonant frequency of that particular atom. It turns out if you keep scanning up and down, there'll be another point in which it happens again, and this time the frequency would be equivalent to the oxygen. And since water has hydrogen and oxygen in it, there would be two resonant points, two exact frequencies in which you'll get the resonant frequency of the hydrogen, and we can detect the resonant frequency of the oxygen. This seems like a simple little experiment, but it turned out that what happened is, in the industry, a lot of ways in which we used to try to measure and test materials was to destroy the materials. We would have to take an airplane, for instance, and cut a piece of the skin of the airplane off and destroy it in various ways. Blow it up, melt it, stretch it, strike it with radiation and do various things to destroy the material to test it, to find out what it was about. But what happened was, when electromagnetic nuclear resonance came along, they discovered that they could test the skin of the aluminum skin on the airplane for fractures or for imperfections by putting the entire hull of the plane into the huge klystron magnets, putting the skin through a magnetic field and then striking it with a radio wave, and by moving the radio wave up and down, they could actually find flaws into the materials when it was cast without destroying the material. And it started a whole new type of testing known as non-destructive testing. Later, scientists discovered that if they wanted to, you were in New York back in the 50s, early 60s, and you went to a place called Famous Amos, and you picked up one of Famous Amos's cookies, and you took it home to your laboratory, and you wanted to find out, well, what makes Famous Amos cookies so great? And if I eat the thing, or if I break it apart and goof it up a lot, I'll destroy the material. So is there some way that I can test Famous Amos's cookie to find out what it's made of? And yes, on an atomic level, you can take the cookie, you can put it in a big glass jar, you can put a magnetic field going in one direction, you can wrap a coil around it, you can put a little radio transmitter on the thing, and you can scan through and find the frequencies, a chart of the frequencies in which you find the resonant nodes of every single atom that's in that cookie. The interesting thing too is that later we were able to detect, when the precession happens, we were able to detect the power of the, when the thing precesses and throws off a radiomagnetic wave of its own, which we were picking up just to find out what the pitch was. We found out that that happened at a certain amplitude, and that the amplitude of the wave could also be measured, and we could tell the amount of material that was in something. So eventually we could test materials without destroying the materials. We could find out every single atom that it was made of, and we could find out the proportions between the atoms. In other words, we could crack the code of Famous Amos's cookies and find out exactly what was in them on an atomic level, and exactly what the portions of the atomic levels were, and be able to duplicate in a laboratory the Famous Amos cookie, and still have the original around to test. This non-destructive testing became very, very crucial. So what happens now is every atom in the electromagnetic or chart, or in the atomic chart, the atomic table, is what used to be 108 when I was in school. It's up to much higher now. All 108 elements had a specific frequency that they would resonate at under a specific Gaussian field. And so if you calibrated your Gaussian field and put materials into a little jar, you could test these materials and find out what the atomic structure of something was without destroying it. This also gave rise to testing live things. We were able to put amoebas into little test tubes, and grasshoppers, and bumblebees, and we were able to irradiate the bumblebees and find out exactly what atoms the bumblebee was made of. Later, they learned to focus the beam very carefully, and first they focused the beam in slices. We were able to take these radio waves that we were transmitting and put them through these little waveguides and make the radio wave as thin as a knife, and to cut slices through things. And later on at Zenith Corporation, Dr. Julian Hirsch and myself worked on figuring out ways of imaging these things, taking these Lesch-Azur patterns that were occurring on the oscilloscope and turning them into some kind of graphic representation. Well, in those days we didn't have computers, so the computers that were available were the huge IBM 360s and 365s, these things that were usually had something like cobalt and were used for accounting purposes, so they weren't very good for science. But around that period of time, IBM invented a new machine called the 1170, which was a scientific machine. It had the ability to do floating point math out to 12 decimal places, and they invented a thing called a touch tablet, which actually was a tablet that had a little pen, little magnetic pen on it, so we could draw on the screen. They created screens. We used to use teletypes, and everything would come out on a teletype on a piece of paper. And then later they developed computer screens. They created what they called XY graphing, pixel graphing, and we were able to create had the first monitors, CT monitors, with touch tablets that we could use to do scientific notation. And with this, we were able to take these charts of frequencies and the quantity of the frequencies and begin to create imaging. So eventually this technology gave rise to what we now know as magnetic nuclear resonance imaging, or MRIs. And you can go into a hospital and sit on a little bed that shuttles you back and forth, and a radio in a huge magnetic field and a radio beam will cut through your body in little slices at a time and display those little slices on a screen as an image, and the colors of the image will be equivalent to the atomic materials that you're made of. And you now can be non-destructively tested. We don't have to take you apart like in anatomy class. They used to dissect the body. We can put living organisms in a magnetic field and shuttle them back and forth and create magnetic images of what's going on inside the body. And with the advent of computers and computer imaging, that has become so sophisticated now that we can now do real-time studies of what's going on inside of people's brains. We can take slices of people's brains or head while they're thinking about something and see the blood flow in various areas and see what part of the brain are lighting up. So when you're watching these Discovery PBS specials these days, and you're seeing these beautiful images of brain scans, and you're seeing these beautiful images, three-dimensional models of the heart actually pumping, and we're looking inside of living organisms and watching them function. This all happened because of, I'd like to think of the science fair project that I did back in 1956, 1957 for my high school, and later on went off into the electronics world to create a career working with Zenith Corporation with Julian Hirsch. We also worked on 3D television. Lasers had been, masers and lasers were invented at that time, and we actually designed and built a laser beam that was a television camera, and then we're able to create laser three-dimensional images and created the first 3D all laser television system. Dr. Hirsch was absolutely a genius. You can look up some of the old abstracts in the library from that period of time, 1961 through 1964. A lot of this work was done in imaging. Later on in the late 70s and early 80s, as computer technology and imaging developed, and the imaging was attached to that. Now, the upshot of all of this is I'm trying to explain to you that with a magnetic field and with a radio beam, we can find the resonant pitch or frequency of a single atomic atom. And that every single atom that is in something living can be drawn out as a chart. So if we think of a times table, now let's say I have a times table. I take 1 times 1, 1 times 2, 1 times 3, and I build a table, a two-dimensional table of columns and rows. And along the top, I put the numerator, and along the side, the denominator. We can build a chart of times tables. And that times tables could be, just the 1's times tables would probably be a single column. Or the 5 times tables would simply be a single column with 10 rows. If I want to represent all the times tables, say up to 10, then I would make 10 columns with 10 rows and put the numbers 1 through 10 along the top and the numbers 1 through 10 along the side, and then multiply them by each other and put in each square the product of that multiplication, and I would create essentially a times table. That times table represents multiplication in the deca or 10 system. I can also create a binary times tables. I can have a 1 and a 0 along a column, a 1 and a 0 along a row, and I can multiply them and put in the squares in between, the product of 1 times 1 and 1 times 0, etc., and create a very small two-dimensional matrix or two-dimensional times table in binary. I can do that in any base system. I can take quinary, or I can take hecadecimal, or I can take octal, where we count to 7, and I can build an octal times tables. With just 2 numbers, a row and a column, we can create a times tables of almost anything. Well, it turns out that if I take the frequency of things that something is made of, I can create a times table with either the frequency, or I can use the periodicity, or I can use the wavelength. And wavelength, lambda, or P for periodicity, or F for frequency, can be notated in a times tables. Anything that exists is made up of atoms. And that atom is generating a frequency dependent on its atomic structure. So if it's gold, and I say I put gold in a certain magnetic field, and I hit it with a radio wave at a certain frequency, that gold is going to process and start generating a little radio wave of its own and say, here I is, and I can say, oh, well, that's the gold atom. And if I have some material, like Archimedes had to figure out if there was gold in the crown for the king, and he did it by volume displacement in water. Today, he would just go to a magnetic nuclear resonance imaging thing. He would just put the crown on the table, and they would do a magnetic nuclear resonance imaging, and they would say, oh, there's exactly this much gold and exactly this much tin. And they could create a times table that shows the number of frequencies, or the atomic molecules, the atomic atoms that are in that thing, and they could also take this times tables and say, well, we have these 15 elements that this thing is made of, and they're in this ratio or proportion to each other. And if we lay out some of those numbers, say the frequencies along the columns, and we lay out the proportions along the row, we can create a times table of the material that is in that crown. If we add to that another number, a third dimension, which is its position or point in space, we can then define any object that exists, anything that is that is real, as a series of frequencies, periods, or wavelengths by its left, right, up, down, forward, and backwards position in space. And we can build a times table, essentially a two-dimensional or a three-dimensional or even a four-dimensional times table of that object. And this times table is known as an Eigen matrix. The word frequency can be translated into eigenvalue. Wavelength is an eigenvalue. Periodicity is an eigenvalue. And I can take these eigenvalues and plug them into a 2, a 3, or a 4-dimensional cube and create a times table, essentially, or an Eigen matrix of that object. So this chair I'm sitting on is made up of certain atoms, and those atoms can be discovered through magnetic nuclear resonance, and we can find the resonant pitch of every one of those and put it in a table. We can take the position of every one of those atoms and put them in a table, and we can take the power or the amount of material that's in every one of those atoms and put that in a table, and essentially I can create what is known as an Eigen matrix, which is a mathematical times tables that describes the object. So the object itself is nothing more than pitch, periodicity, frequency, position in space, and the intensity or the amount. And by using those numbers in a four-dimensional cube, I can create a times table, an Eigen matrix of this chair. This chair has a shape, and the shape would be described by the positions of each of the electrons. That would be part of that Eigen table. This chair has a certain strength, and this would be represented by the types of materials and the amount of within the materials. And this Eigen matrix would be essentially a mathematical equivalent of the that this chair is made of. Every object that exists out there, every that exists, has an Eigen matrix, can be represented as a mathematical table or an Eigen matrix. And that Eigen matrix is essentially what the frequencies of the Eigen matrix are, essentially what our senses are attempting to grab, bring into our brain, and model. So everything in life can be represented as a frequency on a periodic table. It can be represented as position within four-dimensional space-time, and it can be represented by density in that table. And by having the density, by having the position, and having the frequency, period, or a wavelength of the material, the actual atoms in the material, we can say that is a chair. And we can build an Eigen matrix model of a chair. So when you hear people talk about the matrix, what they're talking about is taking atoms and finding out their resonant frequency and putting that in a times table, and taking the position of that atom in space, in four-dimensional space-time, and putting that in the table, and taking the density or intensity or the amount of that material in any particular area, and we would call that atomic mass or the atomic weight. The atomic weight of each element, of course, is different depending on the number of protons, neutrons, and electrons that are in it, and all of those numbers combined together in a nice four-dimensional mathematical cube represents what's out there, or what it is made of. Our brains, our perceptual mechanisms try to pick those things up and move them into the brain and create models, three-dimensional, four-dimensional models of the Eigen matrix. So what the brain is actually processing is a mathematical model based on the resonance of things. The important thing in the physics of consciousness is how is this decoded by the senses. And that's the next thing I want to talk about: reciprocal math. I want to talk about the square root function, and I want to talk about how the Eigen matrices, which are out there, are picked up by the senses and brought in and modeled by the brain, and the mathematics that is used to decode that. So everybody out there, you have a good day, and if you're not having a good day, well, make it better, or I hope it gets better. Ta-ta for now. Out.